This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 157. Hope you're staying cool this summer. The title of today's presentation, GOES Observations of Recent Fires, Big and Small. The presenter, Chris Schmidt, Fire Detection and Characterization Algorithm Lead and Researcher at the Cooperative Institute for Meteorological Satellite Studies, Space Science and Engineering Center, the birthplace of satellite meteorology. We're glad to have the discussion following Chris's presentation facilitated by Jessica Cherry, the Regional Climate Services Director for Alaska. Just a few reminders before we get started. As you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. If you have not signed in with your full name when asking a question in the chat, please make sure to specify it. We will address the questions that are asked in the order they are asked in the chat. Please remember to check your spam folders, as the email system may occasionally reroute Tower S communications there. We don't want you to miss any communication related to the Satellite Book Club or related to satellite products that are available for operational use. We are always looking for future presenters. Please contact the Tower S team, Kashad Bowman, Emily Maddox, if you have a presentation you'd like to share with your colleagues. Particularly if you are giving a presentation at the National Weather Association annual meeting or another annual meeting coming up. Perhaps it's not even directly related to satellite imagery, but touches on it. We'd love to have you as part of the Satellite Book Club and expand our discussions. Also, the training team can help create training materials that may be unavailable. Contact Russ Van Til for information or questions on that. I'd like to thank the Tower S team, particularly Kashad and Emily, the Office of the Chief Learning Officer, GOES-R and JPSS programs, our facilitator, our presenter, and all of you for being with us for today. Without further ado, let me introduce Chris, who's a researcher, as I mentioned, working at CIMSS SSEC at the University of Wisconsin-Madison. He has been working on biomass burning since 2001 and is the algorithm lead for the current operational fire detection and characterization algorithm, as well as part of the next generation fire system NGFS team. Chris is a repeat presenter at the book club. We're glad to have him back. Chris, take it away.
Thank you, Jordan. I'll apologize up front if you came here looking for wildfire or fire weather, as the original title suggested. That was just me being slow and giving them an update to our placeholder. I figured I'd rather talk about things that interest me rather than things that might interest other people. So I'm going to be talking about GOES observations of fires, big and small, obviously. And this scene happens to be from 2 years ago, not from last week, but it could well have been given how things have been going this summer. So ABI fire detection, as you may know, ABI is proving to be a capable fire detection and monitoring instrument. The current baseline algorithm is the fire detection characterization algorithm, which is based on the wildfire automated biomass burning algorithm that was developed at SSEC. The names are often used interchangeably, and at this point in time, they're pretty much the same algorithm, although they will start to diverge in the near future. It provides fire detections, fire rate of power, FRP, fire size, and fire temperature at 2-kilometer resolution for all ABI scans, FOLDIS, CONUS, and MESO. You have it in AWIPS. What you get in AWIPS is those characterizations and then the fire classifications. There's a mask that you don't get all the pieces of, which we'll be talking a little bit about. Also, thanks to recent investments by Congress, finally, NOAA is developing a new next generation fire system by Mike Pavlonis, and that will be providing fire alerting capabilities driven by an updated algorithm. It shares general background history with the WFABA FDC, as do pretty much every other fire detection algorithm, but has many significant changes and updates. The loop on the right is the Marshall Fire, which you may recognize from the last time I spoke here, but I just wanted to reuse it because it's a nice little 4x4 animation of the 16 ABI bands during a fire, where you can see various things happening. Band 7, which is third from the left, second down, where you can see the fire hottest there. But the fire does tend to show up in many other bands too. And if fire's hot enough, you can see it in practically every band. There have even been occasions where a fire has shown up in band 1, the blue band 0.47. In this case, that's not actually the fire you're seeing, that's reflection off a smoke plume. The fire wasn't quite hot enough to show up in those visible bands, but it does happen. So what does this talk about? Well, our understanding of the capabilities of ABI with respect to fire detection continues to evolve, as does the user base and their needs and desires. They're figuring out what they want and what they can do with the data that they're given. Paul Menzel used to tell his satellite meteorology classes that one person's noise can be another person's signal, and that is certainly true with fires. Because the ABI sees thermal anomalies of all kinds, and if you're just looking for the highest risk impact ones, you're not going to care about a lot of, say, the prescribed burns, for example. But there are people who are doing work in aerosol modeling who are going to want to catalog those. And skilled human operators are finding things that are remarkably small, and new algorithms, especially the NGFS, is starting to pick up some of those too. And so we need to better understand what we're seeing and what they are and what we need to do with them. User needs and expectations do differ. That's part of the art of the fire detection monitoring and alerting, and it's identifying which fires are going to be an immediate hazard, as I said, and which we're going to need to track for other purposes. The line between good to know about and absolutely need to know right now is very contextual for the user. So I'm going to look at the recent fires in Maui and two other cases that were not nearly as, quote, important, unquote, but they show us about the abilities that ABI has. So this loop, and I'll apologize right now, I didn't use AWIPS this time around. I made custom imagery because a lot of stuff I wanted to show I couldn't do in AWIPS, unfortunately. But we know about Maui having drought conditions and the fires that occurred a couple weeks ago. And we know there was a red flag warning issued in advance, and they had high winds. So what did GOES see? Well, the loop on the bottom is the 0.64, not the 0.86, I mislabeled that. The 3.9 micron, and then the fire metadata mask from the WFABA/FTC. Well, what do you see on that mask? You're seeing the fires. So the red is fire detected pixels. In the middle panel, the darker pixels are the fires. And the left is obviously just visible, but you can see where the clouds are. And if you pay attention, especially to that middle panel, which I hope is presenting well over the internet, you see the fire on the right. That is the one that's upcountry that started earlier in the sequence. And then you can see the Lahaina fire. And if you pay close attention, you'll see the Lahaina fire kind of warms up a little bit and then disappears, but the FTC doesn't see it. And then it takes off later. So let this finish up one more time. There it popped up and disappeared. And the firestorm is coming in a moment. And that mask disappears on the right because of the solar blackout zone, by the way, when it goes all gray like that. So FTC picked up that upcountry fire, as I said, but it didn't really see that Lahaina fire when it first started. And so the circle highlights where that fire pixel shows up, that warming, and it's difficult to see, I'll grant you that, but it is there. I believe NGFS, when we did a rerun for this, did pick it up, but I didn't have that data to show. So it was low magnitude, didn't reach the detection threshold, but perhaps most importantly, local emergency management tamped it down pretty quickly. And we don't have a specific cause for it yet, but it was probably a power line that fell. If we look closer at the ABI data for that time period, we can maybe tease out a few things. So the top row is that 0.64 again, not the 0.86, 2.2 micron, which is the shortwave IR, and the 3.9. It's scaled a bit differently this time. It's scaled kind of a min-max scaling. And what you can see with that upcountry fire is you'll see a signal in that 2.2 micron that corresponds with the one in the 3.9, and we see a little plume. That signal from the Lahaina fire is really, really not very strong at all. So the bottom panels are brightness temperature difference between the midwave and the long wave, then a radiance difference in the midwave space between the midwave and the long wave, and then taking that radiance difference and subtracting off the rolling average of the previous 5 frames. Why do I do that? It helps to detect those changes, especially when things start up. It also is really good at finding clouds. You can see there's a lot of what looks like noise in there, but that's really correlated with the clouds. Another thing to remember about ABI data is nav's not always perfect. You can see the image jumps at one point during this particular sequence, which is unfortunate given what was going on, but that is a reality of life with a satellite. So just to give you an idea of where that fire originally started, there's Lahaina, and it was up by the now infamous Lahaina Intermediate School. And I would take a closer look at that location. And there's basically a ditch in an old plantation along the Lahaina Luna Road across the Intermediate School. There's a substation nearby, which actually was not affected by the fire, and it doesn't appear necessarily to have started it. But there are power lines along the road and along the ditch. And that ditch is pretty relevant. It probably is why things blew up later, because it's wooded. So looking later in the day then, when things blew up in Lahaina, the fire crews had suppressed the brush fire and they were apparently reassigned. I'm working off of secondhand information at this point. None of this is necessarily proven. Take this as initial analysis. The story is that there was one mini pumper left behind, which is basically a pickup truck with a couple hundred gallons of water and a pump to work on small flare-ups. This may or may not be true, but it came from firefighters who were out there vacationing out there, California firefighters. And they were supposed to watch still smoldering remains. Ground reports at the time indicated that at 3:10 local time, there was a small plume of smoke, but by 3:20, it got a lot thicker. A gentleman across the street was videoing it around 3:20 to 3:30, and that's when things were taking off. Now, here's what's interesting about this. The GOES started to see a warming at what would be the 2:56 local time, PM, the 056 UTC scan. And that's interesting because we usually think of GOES as lagging behind people on the ground, and there were people right there watching the fire, but we have observations that say that it didn't start ramping up until, let's say, at the earliest 3:15, 20 minutes earlier, GOES is seeing an increasing thermal signal that doesn't correlate with clouds, for example. You can see in the viz, there's no clouds over that location, the sky's clear. And then within a few minutes, it blew up and turned into the firestorm that we know. So zooming in on that time period, just to highlight that hot spot, you can see, if you look at that 3.9 in the upper right, there's a little bit of a darker spot. If you look at the, excuse me, lower left, what's highlighted, there's a little bit of a redder spot. You can see it's warmer in that radiance difference, and it really shows up brightly in that difference with the rolling average, which is what it's intended to do. And if you kind of visually match up where the clouds are with that feature, you can tell that, yeah, that is not matching up with a cloud. That is something else. That's thermal. So by 3:21, by the time it was reported, by the time it was seen by the guy across the street as being a problem, GOES had an inarguable hotspot. It was showing up in the 2.2 micron. It was detected by both algorithms. It was, or maybe they detected it 5 minutes later. I think one picked it up at 21 after and one picked it up at 26 after. But they all basically saw it at the same time as people on the ground. And perhaps more importantly, there was no question in the GOES data that something was happening there. So what we saw there was that with the reported start time of the fire, the initial fire, we could see that it was virtually contemporaneous with the heat signature and the raw data, at least. Now, the operational algorithm didn't pick it up at that time, but the signal was there. When it reflared in the afternoon, the algorithm picked it up at the same time as reported on the ground, but perhaps more importantly, the actual radiance data, had it been observed by an expert, would have seen the flare up before it was reported, several minutes before it was reported. And that's where that wooded ditch comes into play. It wouldn't have been as easy to see from the road, but that's where things could have started to flare up. Smoke may not even been so obvious at first, but in those high winds, it would have been a perfect place for that to happen. That's a hypothesis at this point. I'm sure there'll be reports about that in the future, but based on the information I have, that seems to be the most likely scenario. Another thing to note about the operational algorithm, you see those green pixels, you see the blue pixels, you see the blackish pixels. Those blue and blackish ones are blockouts. And so some of the fire activity on Maui during this event actually occurred in those locations, and the operational algorithm never saw it. This is an improvement, however. If some of you remember a year or so ago, we didn't have coverage over Hawaii at all. So good thing we got that going last year. Now we switch gears and talk about smaller fires. We see a large number of thermal anomalies with ABI, as I said. Some are reflections off of solar panels or even water, heat from heat islands, urban islands, steel mills. There's all sorts of things that can do it. There's a large number of low amplitude, short-lived thermal signals that are indeed fires of some kind, but they don't have an immediate hazard impact. And we often don't know what they are because there's really no obvious reason for them. So, and sometimes the public will take notice of them, sometimes they won't. And so as part of the NGFS development, I've been investigating fires that appear to be false positives or were otherwise perplexing. In other words, this is the fun part for me that may be boring for you. Back in February, I saw some fires near the Chicago suburbs where I grew up. I didn't expect to see them on February 13th. There were several. Now, along Lake Michigan, there's a couple hot spots, but those are steel mills. But those other guys, what the heck are they? So this particular display came out of that NGFS in real Earth. This is one of the prototype things we're working on. Not something you can necessarily see yourself right now, but it's changed since I took this screenshot. But this has terrain corrected pixel locations in it. So I did a little digging and discovered that, you know, despite the weird time of year, the Forest Preserve District of Cook County, I should say, was doing prescribed burns for the first time in at least the 30 years that the director had been there. And it could have been even longer than that. So they may never have done burns in February before. He was able to provide me with a perimeter estimate for one of the fires, unfortunately none of the times for it. And so of those 6 hotspots, 3 were prescribed burns at Forest Preserve sites. One was a private nursery, who I was also in contact with, and then those steel mills along the lake in Indiana were showing up. And they are, by the way, correctly flagged by the NGFS as being steel mills. So if you're looking at that data, it tells you, oh, these are steel mills. So zooming in on that one fire I had the perimeter for, this is up by Deer Grove, Illinois. Before I knew it was a prescribed burn, I was trying to figure out what could have done it. And there are large buildings there. It could have been a large fire, but that would have made the news. This is a Tony area. Nonetheless, I did connect with the fire department there, and they said, no, that was this prescribed burn. And sure enough, it was. And the blow up on the right shows the area that was burned, which is basically the swampy area of that portion of the preserve, which is an old Nike site, by the way. And the land is pretty much square in the middle of those 4 pixels. So it was a nice validation of the navigation and of the detection capabilities. Like I said, I didn't have a good estimate of when it started and stopped, so I didn't look at that, at least for these purposes. However, the Pizzo Native Plant Nursery folks did tell me when the fire started and stopped, and so I was able to look at that. And so here's just what that looked like on the map. Outline of the burned area, which was kind of right on the edge of those 2 pixels. So it makes sense that it was picked up in 2. And there's a fire of the folks late in the afternoon, a picture of the folks late in the afternoon as it was burning. So you can see there was a decent flaming area going on at the time. Now, this is an eye chart, I know, but I needed to kind of magnify things to pop out the signals for us. The top row is the 1.6, the 2.2, and the 3.9 microns, so different shortwave bands. And this is during the late afternoon, so those shortwave bands are still showing the sunlight. And we're going into evening as the loop goes through. On the bottom, we have that brightness temperature again, midwave versus long wave, the radiance difference again, the radiance difference over time. And what do we see? Well, I was told that basically the fire started around 20 UTC and ended around 24. We don't start seeing it until almost 22 UTC, and it doesn't really pop until almost 23. Why is that important? Well, the fire was pretty consistent in size and power over that time because it was a nice controlled prescribed burn, but the background was really hot from solar reflection. You can see that in the bottom right. As the loop progresses, that minimum temperature drops. It starts out around 5 Kelvin and it drops down close to 0 and below 0 after sunset. And the fire pops out as that occurs. And so basically this is an indication that we need to be mindful of that effect on our trend analysis and trend monitoring, that we lose information because, well, frankly, the sun is a bright thing shining on a reflective surface. and it hides our fires at some times. As far as the difference between a threat and a curiosity goes, back on July 27th, there was a strange alert that I caught that I was thinking this must be a false positive. I knew it had rained in this area. It was showing signal, I had the time wrong there. It was actually 1:55 a.m. That's 6:55 a.m. UTC. It had rained in the area a day or so before, not breaking the drought, but it put a dent in it. But it was suspicious, like this shouldn't be a fire. Well, it was. Here's again the same loop, same kind of loop looking at that time period. And it's not as obvious because this was a smaller fire. We see a signal pop up in the 1.6, the 2.2, and the 3.9, and in the radiance difference and the brightness temperature difference. It's short-lived, but it shows up, for the thermal signature shows up at about 6:26 UTC, 1:26 local time, maybe even 5 minutes earlier if you're really creative. And it was shown that it was within this footprint. So what the heck was this thing? And I should note that the time that the NGFS reported it was, I believe, 1:55 a.m. So what it was a home, and you can see a picture of the burned out home to the upper right and what it looked like from Google Street Map beforehand. It was this house burned down, and the firefighters responded at 1:25. It isn't clear if that's when the call came in or if that's when they got there, but that's the same time we first saw it with GOES. And no matter when they got there or how it was reported, which is information I hope to get, it was not a particularly large fire, and we still saw it. Had it not rained before, had this been in a red flag warning, it was in a red flag warning a week or two prior. This case study for ABI sensitivity could have been a case study in ABI detecting a threatening situation. And this is why those little things matter and understanding them matter, because even to me, the guy's been doing this for 20 years, it at first looked like a false positive. And so here's looking at the map. I've drawn a circle around the house so you can see it relative to the pixel. That's the terrain corrected pixel footprint. It's just on the southern edge, and if you were to go back and look at the loops, you would see that, oh yeah, it does kind of flop between those two footprints. So technical details matter. ABI was designed to balance dozens of requirements, of which fire detection and characterization are a small fraction. When GOES 17 and 18 were taking data simultaneously, that allowed some comparisons, which will be the last thing I'll walk through really quickly. We've never been able to do this before. And so we were lucky enough, if you will, to have Kilauea pop up in early January. It had a nice 1 kilometer diameter lava lake, so very well-defined heat source. And that would fit well within not just the nominal ABI footprint, but the actual sample size, which is smaller than the pixel size, believe it or not, before it's remapped. Would fit well within one, although it could straddle a couple. So here we go with the comparison. We have the first column is GOES 17, second column is GOES 18. They look very similar. Well, there's the difference on the right, and there's a lot of little differences. When the heat source actually appears from Kilauea, we can see there's some pretty bright, pretty big differences, plus or minus 30 Kelvin, give or take. And since it saturates out on both sensors pretty quickly, we don't really know exactly how much difference it really was. Why is it scintillating so much? Why is it changing so much, even though it's a very stationary heat source? Well, that's all the little details that matter. That's the wobble of the satellite. That's exactly where the samples are landing when they're taken. That's how the resampler modifies them. That's to some extent atmospheric effects even, because we're talking about intense heat source. There's even something else going on if you're really particularly eagle-eyed, looking at that difference column between 17 and 18. And the 3.9 micron, I forgot to mention that, it's Viz 3.9, 11.2. That 3.9 micron, there's a warm spot to the right of Kilauea, which means that it was looking warmer in GOES 17 than GOES 18. And my hypothesis for that is that it was some sort of internal reflection on GOES 17. Like we're talking super detailed issue. Would that matter in operations normally? Probably not, but it's interesting from a technical perspective and the kind of thing that might show up in the future, the weird things that happen with these satellites. So a few things stood out for me, only a few. I won't read through them all because we're running low on time, but there's that hot spot to the right of the of Kilauea highlighted for you. You can see it's not really there in GOES 18. So could that be It's not detector memory. If it was detector memory, it would be a smear, given the way ABI works. It's a reflection of some kind within the satellite telescope. So we continue to learn more about ABI's detection capabilities. We're repeatedly seeing cases where fire reports from the ground are nearly contemporaneous to detectable signal ABI data. Whether or not that's something that the algorithm finds or is inarguable is another question, but it is saying that better sensors, and I mean by that bigger telescopes that give us higher resolution pixels that are well sampled, could transform those interpretation cases to inarguable ones, even from geostationary orbit. Why am I saying bigger telescopes, well sampled pixels? Well, GeoXO, the specs I've seen, has basically the same telescope as ABI, so we're not sure what the advantage will be. It'll take more time and understanding what the GXI instrument will be before we'll know exactly how much better it will be than ABI. We're also seeing that filtering fires by risk category will be a challenge. It's very contextual. Sometimes requires localized knowledge. That house fire in Iola was a curiosity. That same house in San Bernardino during a Santa Ana event is an existential threat. So being able to pick it out is important. Knowing it's there is important. What you do with it, that takes another step of analysis. So there's a lot of work left to be done, and thankfully it's been prioritized so we can get to do some of it. And that's my talk.
Great, thank you, Chris. Lots of very timely and interesting information there. I encourage everyone who is here to stay on for a few minutes to engage in a short discussion with Chris and our community here. So thanks, this has been great. Go ahead and if you have questions or comments, you can put those in the chat. And I'm going to start off with a few questions here, Chris. We had one very specific one from Jordan, which was, do you know what Himawari saw in Lahaina during the Maui fire?
I am horribly embarrassed to say I have not even really looked at it yet. Although part of the reason is I'm not as able to pull it into IDL as I can the standard ABI data to do those analyses I was doing. But I could have looked at it in Mercatus at least. I didn't even think of it. Thank you for reminding me, Jordan. It's easy to forget it's out there sometimes when you're so focused on certain tasks.
No worries. I'm sure you'll be presenting this slide deck to a number of folks, and be interesting to know what it saw. So I guess a question from me. So you showed the potential early detection, with on the order of, I think, 20 minutes or something before of the hotspot in Lahaina before it blew up on the ground, according to these different time steps. So how would you potentially warn the emergency managers, or what would potentially be the flow of information that could have taken that improved detection and used it in the field for decision making? Is that just like a hopelessly short window, or can you imagine any sort of alert that could have gotten to those folks from that improved detection?
Well, the funny story is, not so long ago, before all the money started flowing, I was asked to figure all that out myself. Is way too complicated thing for one person to do. Thankfully, now that's a focus of the NGFS and NOAA's initiative, and there's also other initiatives, although they're not focusing on GOES so much, that are trying to take this fire intelligence, make it actionable, and make it timely. And it is a hard problem. And again, it depends on your users too. For example, one of the systems that's in place right now, there's a whole network of cameras out west that are basically designed to watch ridge tops for heat signatures. Or for, sorry, not heat signatures, for the smoke plumes. And some even companies have AI systems to detect those smoke plumes and trigger alerts. And there's a constant tension between the end users, particularly places like CAL FIRE, who don't have a high tolerance for false positives, and systems like that, which can throw them, although they're getting really good at not, because they have a lot of data they can kind of bring together. So there's a lot to develop in that realm. and a lot of learning to do, both for the developers and the users. So there's not going to be a simple answer for that question, unfortunately. But we're getting there. I mean, just providing the data in a usable format is a step forward. It took years for the NWS to see fire data. It took years to get the mask into AWIPS. You know, we didn't even have a GIS available, GIS capable format until NGFS came along. There's a lot of steps to go yet, but I can envision a day where your rural fire department might want to keep an eye on something like the NGFS or even its successor, to say, okay, we know we have a big area, things can happen, we see a suspicious spot, should we check it out preemptively because it might get worse before anybody reports it? You know, that's a specifically a big problem in the plains when it's windy. Our friends out at the NWS office in Norman spend time watching the raw data and the products for fires in spring especially, and they will call local emergency managers and tip them off that they see something suspicious. And they were the first ones to actually see a house fire and confirm it.
Fantastic. Yeah, I have a couple more questions, but let's go ahead and take a couple from the audience here. So from Matt Gunshar, is there something unique about Hawaii that causes blocked out pixels? Where else in the US do you see that? And do you see a solution for that down the road?
Sure. Well, it's not unique to Hawaii. The blackout that showed up in that loop where everything went gray was a solar blackout. The WFAB and FTC have this thing where basically the area where the angle of incidence meets the angle of reflection within a certain cone and the area that's the solar subpoint are blocked out. Because when this was first developed for South America, boy, all those little water bodies would flash up and they were impossible to deal with. And so the blackout was developed to get rid of them. Is it perfect? No, and NGFS doesn't have something like that. It has a more nuanced way of dealing with it. So that particular thing is going away. Another thing that can go away is the ecosystem blockouts. Again, WFABA and FTC make this assumption about certain ecosystems that it can't process them. That's not necessarily the best assumption to make. That's why we didn't see Hawaii for a while, because the data set was missing Hawaii. We had to put it in by hand. That goes back to decisions somebody else made in the 90s. So don't ask me why we didn't notice for so long. That can be made better too. So you can reduce those effects. You know, they become more nuanced in the sense that some things will get blocked out because we know they're persistent anomalies, but you might have an actual fire happen there anyway, but it won't be nearly as big a problem as it is now. A fun thing about doing fires over the water, though, is we've discovered that there's more cosmic ray strikes on the detector than we were aware of, because NGFS started picking up stuff over the water that looked like a decent fire, and it turned out to be, it was just detector noise that got remapped in, so it looks like a fire, even to human eyes. But it's only present in band 7, so we can filter it out.
Great. Well, there's been another question and comment in the chat about day-night band. Have you personally had a chance to look at it? I know that Scott Bachmeyer said there's some examples on the CIMSS satellite blog, but maybe you could comment on that as well.
I hadn't spent any time on that because I know people like Scott did look at it, and I glanced at it. I do look at it sometimes, but my focus lately has been trying to sort out these questions of earliest detection and verifying whether something was a fire. And I'll end up going to VIIRS or MODIS or DNB when I need to. It's often not the first place I go because of the time difference. You know, there's other folks that are focusing on validation of NGFS and FDC against VIIRS, for example. And so I don't put my time on that specifically. I mean, I have looked at it. It's not my primary focus.
I guess another question for me, just because you've taken the time to do this thorough analysis and this example is so recent and so raw still, have you had a chance to brief out emergency managers in Hawaii?
I wouldn't even want to try until we have a better understanding of what actually happened. We may find out that they knew it was flaring up when GOES saw it flaring up, and that's great. I don't want to presume to know that for sure. What I wanted to show though was that we could see that based on people on the ground who were right there, they didn't know it was flaring up. There's a video, I had the link, I couldn't share the video unfortunately, but the link to the video was in the presentation. There was somebody right there watching it and they didn't see it flaring up at the same time that the GOES did. And that just means to me, that means it's possible. It's something to keep in mind for future development of algorithms and satellites, that this is something we actually can do with GOES. It's not out of the realm of possibility for a geo to do that. So I'm trying to get back to that page that had the actual.
I'm just wondering if your analysis would actually be useful in the event forensics.
Oh, it could be, yeah. When it gets to that point, it could be. I would not rush in right now because it seems like it's politically fraught on multiple levels. The emergency manager quit, and there were questions about what they did. There was no mesoscan for hours until after this thing flared up. It would have been interesting to see the 1 minute imagery of that flare up. Would have given more confidence too in that, yeah, we're seeing this flare up. That's one of the problems with intermittent imagery, obviously, is, it could have been noise, it could have been that nav shift, like something. These weak signals can be a little tricky like that. So having them consistent over time is a great bit of validation. And I see Yvonne correctly mentioned that the VIIRS I-band operational product, it did detect the Maui fires, and that's on the JSTAR mapper. You can see that.
So I guess a couple, continue to put a couple of questions here in the chat if folks have them, or comments or links to other products. That's fantastic. We have a lot of experts on the call, but maybe you could just say a few words for those who are working in the WFOs or other data users here. Just remind us kind of what the plan for the next generation fire system. How, in what ways are those significantly different? How is this going to be a big step forward?
Sure.
Is it focused on detection? Does it include an engagement with users and emergency managers? I don't want to steal Mike's thunder here, but it'd be great just to remind us since we're on this topic.
Yeah, I certainly don't want to either, but hopefully he trusts me to relay information reasonably accurately. The first thing to remember is it is under development, and this was the first year it was running it is running in the test bed right now, I think, or is going to soon. I think it did start already. So that there are users who can actually see those outputs in real time, see the alerting outputs, and things are being tuned like crazy left and right as we sort things out, not with just the algorithm, but also how do you present the data, how do you move the data. How is it different from FDC? There's a couple key differences. The key similarity is that they both work on that mid-wave, long-wave difference primarily. And so at their heart, they've got the same thing going on. But there's additional steps in NGFS that represent an improvement over FDC, which was basically designed for GOES 8 through 15. We didn't get a chance to do much to it when we moved it over to GOES R. That's why the new investment was so important. So it was the NGFS is based off of the Volcat alerting system, because it has alerting integrated. That's helpful. It has a temporal component, a bit more of an advanced one than the FDC does. It can pay attention to things over time and use that to help raise or lower its expectations of what was actually happening. It manages clouds much better. FDC tends to just give up at a certain point. It'll detect fires through clouds, but it doesn't try to do anything special to the clouds. NGFS does a better job of correcting for transmission losses to give you a smoother FRP signal through clouds when the fire is still visible anyway. It is more sensitive, although ironically that doesn't always translate into earlier detection for the big events, because most of the big events flare up so fast. That increased sensitivity that allows it to pick up the house fire at night that FDC will miss doesn't matter as much because the fire heats up so much in 5 minutes. We'll probably get a better understanding of how much better it is for that initial time of detection as things go forward. For the medium and small events, it can beat the pants off the FDC because of its increased sensitivity. So, you know, it has advantages there, but we're still understanding, still sketching out what that actually means in regular use. And because of that higher sensitivity, it is finding that other stuff. It's finding all the little ag burns, and there can be lots of them. It's finding all sorts of sources of false positives sometimes that we weren't really paying as much attention to perhaps as we should have. And so we're dealing with that. Does that cover what you're looking for? I mean, so
Yeah,
I
and
don't mind, unfortunately, because I'm not sure when it'll go operational.
right. To keep pulling on that thread then, you know, for GeoXOs, GXI, what differences are we going to see there?
As I understand the specifications now, the aperture of the telescope is basically the same. Focal length is probably basically the same, but the detector size will go down, which means that the sampling resolution will go from 2 kilometer to 1 kilometer. Hopefully we'll be able to do the data without the remapping, but either way, we'll just stick with the remapping resolutions for now, the 2 versus 1. On paper, you'd think that's a factor of 4 improvement in the detectability, but the diffraction spot doesn't change if the telescope doesn't change. And we'll go from undersampling it in the current situation, which means that a lot of the energy falls into that detector. It's like 85 or 90%. It's crazy high on ABI. But on GXI, because it's going to be taking that same diffraction spot but putting a smaller detector on it, that number is going to drop. I'm not sure what that number is exactly. Let's say for the sake of argument, it's like 60 or 65. That means that we'll still pick up some things. We'll pick up things better, but it's not going to be as much of an improvement as a 2 kilometers to 1 kilometer suggests. However, during the process of actually going through everything, they might change the specs to improve that. So I'm just urging caution now that it may not be quite as big an evolutionary loop as we'd like. It will still be a leap, which will be good. So, and there's also more information available from GXI, just in general, higher resolution and other bands that will help.
Great, thanks. And one of our friends from Sierra has posted the Himawari 9 view of the fires on Slider. So we'll capture that link that's in the chat too. Maybe the final question here before we start to wind down. We talked about spatial resolution, temporal resolution on EXO. This leads to the question: would a bunch of detection on from small satellites, would that make a difference if we really change the constellation?
Well, so if you're trying to do early detection, the key is your temporal refresh. You want to keep looking quickly. And the problem with small sats is to do that with small sats, you need a lot of them. We're talking Starlink scale if you really want to do it at the time scale Geo does. Some folks think that a 10-minute refresh could be good enough, but I think there's an erroneous assumption about what you can see and when you can see it. There's a limit to how much you reduce that resolution before you really gain anything for early detection, if you follow. The difference between a 2 kilometer pixel and a 100 meter pixel is substantial, but we can see house fires with the current 2 kilometer GOES. There's no way optimized for fire detection, really, not really optimized for it. So compared to current GOES, you can make an argument maybe they're worthwhile, but I don't think their best use is for early detection. I think their best use is for mapping of the event at a higher time scale and a higher resolution than you can get with the GOES. Let's say 30 meters every half hour or hour would be fantastic. It would be at the rate that the guys on the ground could use it. That's a case where you don't necessarily need the multiple looks, because you have the acuity there and the resolution to say, yep, here's the fire, and it'll be a reasonably sized constellation that could point at the events you want to point it at, preferably, instead of trying to cover everything.
Right.
That's my bias anyway. And
okay.
It's a somewhat contentious topic in some circles.
Yeah. Well, excellent. I see Jordan's popped back on here, and we do want to announce the a week from today. I don't know if whoever's driving the slides could put the slide back up about next week's seminar, but August 31st at 12 noon Eastern Time, Linda Hembeck, staff scientist from Science and Technology Corporation, she's going to discuss enterprise algorithms and new products for the GOES-R 16, 17, 18 ground system. The TowerS team who organizes these things is fantastic, super organized. If you have any questions, Kashad Bowman or Emily Maddox are the two to contact, or you want to give a talk or suggest a speaker. Jordan, do you have a follow-up here?
Other than to highlight that second bullet, we're in the process of moving over to Slack, so continue to contact our TowerS team in the manner that works for you. But if it's all right, I'll take it from here and just wrap it up. Thank you, Jessica. Thank you, Chris. Thank you to all of our attendees today. Really appreciate it. And as Jesse said, hope to see you next week as our Satellite Book Club continues. Until then, especially you, Chris, stay cool. That heat wave has still got CONUS in its grips.